Hi, I'm Wade from Confluent. In this video, we'll be discussing how to work with keyed state in Flink. We've been focusing on stateless operations so far. These operations treat each message as independent. They don't worry about past or future messages. However, there have been some exceptions. The reduce operator looks at the previous message and combines it with the current message to produce something new. But reduce is a relatively simple operation and is only looking at two adjacent messages. What if we wanted to do something more complex that involved a deeper history? Let's consider the example of fraud detection. If you've ever had your credit card temporarily denied due to an odd pattern in spending, you'll know what I mean. Credit card fraud detection doesn't look for a single transaction. Instead, it looks for patterns in the transactions. For example, making a single small purchase to test the card, followed by a series of large purchases. In this sort of situation, we need to be able to keep some kind of state that persists beyond the current message. It might be as simple as setting a flag, or it might be a more complex object that is several layers deep. If our streaming operation is windowed, we may even need to persist the state beyond the current window. Flink offers built-in support for stateful operations. It includes a mechanism for storing state that is both durable and fast. It does this using an embedded key value store. The keys are determined using the keyby operation in Flink. One of the advantages to this is that Flink also uses keyby for distribution and parallelism. Ensuring these keys match means the state can be kept local to the task manager. This allows for in-memory caching and speeds up disk access. Essentially, it prevents the necessity for slower network hops. Flink supports several different types of state storage, including value state, which stores a single object, list state, which stores a list of objects, and map state, which stores a map of key value pairs. Just remember, the state is already keyed using the keyby operator. The intent of the map state would be to handle objects that include a secondary key of some kind. Flink also supports more complex states, such as reducing state and aggregating state. These will automatically combine states based on a reduce or aggregate function. To use our state, the first thing we need is a state descriptor. It contains a name that uniquely identifies the type of state we will be storing. Think of it like a database table where the descriptor identifies the column and the keyby operator identifies the row. The descriptor also defines important details about the state itself. This is dependent on what type of state you're using. For value state, it's simply the class of object that will be contained in the state. For reducing state, it includes the class of object, but also the reduce function that is applied on each insert. The descriptor also contains other functionality, such as setting a time to live value. This allows the state objects to expire after a certain period. Usually, the descriptor is initialized once when the function using it is created. Often this would be done by overriding the open method in a keyed process function or similar. Once we have our descriptor, the next step is to make use of the state inside our keyed process function or whatever function we are implementing. The state is available through the context object in this function. It provides two different storage mechanisms. Window state persists only while the current window is open. Once the window closes, the state will be cleared. Global state persists beyond the life of the window. This is useful when you have state that needs to persist even after the window has closed. To get access to the state, use the getState method on the state store. This returns a container for the stored value. The actual value can be obtained using the value method. Be aware that if this is the first message for a given key, then there may not be an existing state object. In that case, you may get back a null, and you will have to handle that appropriately. The state object also contains an update method for updating the stored state. Keyed state can be quite powerful. However, it does require a bit of caution when using it. If your key space is large or even unbounded, and you aren't careful, you can see an explosion of state objects. These objects can eat through your disk and memory. This is especially true when working with global state rather than window state. You can mitigate some of the risk using the time to live settings. Otherwise, be careful to use window state where possible, and when using global state, try to keep your objects small and your key space limited. Now let's try these out in an exercise. If you aren't already on Confluent Developer, head there now using the link in the video description to access the rest of this course and its hands-on exercises.